Welcome back to the deep dive. We take stacks of research, articles, notes, and, well, we boil it all down for you. Today we're looking at something pretty fundamental: bridges. And specifically, a really common, maybe overlooked problem with traditional bridges, those expansion joints.
Yes, the bumps in the road.
Exactly. You know the ones. They're expensive, they need constant fixing, and honestly, they can even make bridges less safe, less durable over time.
It's a huge headache, really, for anyone managing infrastructure, but what if you could just get rid of them?
Get rid of the joints.
Yeah, that's the idea behind integral bridges.
Yeah.
No traditional joints. And the advantages are pretty compelling. Lower costs over the bridge's life, better durability, improved safety, even better performance in, say, earthquakes.
Okay, so integral bridges sound great, like a real step up.
Uh-huh.
But engineering is never quite that simple, is it? There are still challenges.
Right. Even with integral designs, the tricky bit is often where the main girder connects to the abutment, that big support at the end.
That connection point.
Exactly. You've got things like concrete shrinking and creeping over years, steel girders deforming differently, plus all the stress from traffic and temperature changes. It can lead to fatigue, cracks, especially in older connector types. It's a complex spot.
And that complexity brings us right to today's deep dive. We're digging into some new research by Zhejiang and colleagues, looking at a really novel approach.
Yes, using something called composite dowels in these integral bridge abutments.
These abutment dowels. Okay.
We're going to unpack how this new structural scheme works, how it improves on what's been done before, look at how it fails, which is always revealing, and get into the science behind why it performs so well. Should be some interesting engineering insights.
Definitely sounds like it.
Okay.
Let's get into it. So integral bridges, they're already seen as a good move. You mentioned the benefits, cost savings.
Yeah, and it's not just theoretical. In the U.S., something like 27 states already recognize that jointless bridges are more cost-effective. The trend is definitely there.
And a big part of making these work, especially the integral abutment bridges, or IABs, is the piling, right?
That's right. Often, H-shaped steel piles are preferred. They have this great combination of flexibility and strength, which helps accommodate that horizontal movement you get.
Movement from temperature changes and loads.
Exactly.
Yeah.
And people are even looking at soil interactions. Some studies show if you put compressible stuff behind the abutment, it can actually reduce the shaking that gets up to the bridge deck during an earthquake. It's about making the whole system more resilient.
So the piles are foundational, literally. But that critical spot remains the joint, the girder to abutment connection.
That's the weak link, potentially.
Hey.
Traditionally, engineers use things like stud connectors or maybe perfobond strips,
All right.
but they all have drawbacks. Stud welding isn't easy. Perfobond can make it hard to place rebar properly. You get these dead zones where concrete doesn't flow well, and welding fatigue is always a worry.
Lots of little problems that add up.
They do. So how do you get around all that? That's where these composite dowels come in.
Right, the focus of this research.
Yeah. The beauty is they don't need specialized welding. And they seem to work really well even with lower strength materials, which is interesting. Plus, previous work already showed they hold up well against fatigue. It's a smarter way to connect things.
And this specific study, they propose a novel scheme using these dowels with a special kind of girder.
Yes, a modified Verbund Fertigteil Traeger MVFT, for sure. It's basically a prefabricated composite girder designed to integrate seamlessly. But the really clever part, I think, are these CL-shaped connectors. CL for clothoid.
Clothoid shape, what does that do?
Well, their shape is open. It means you can literally thread the reinforcing bars straight through them.
Oh, I see. So no more struggling to get rebar around the connectors.
Exactly. It solves that rebar penetration issue and gets rid of those concrete dead zones. Plus, they're designed to be ductile, and they place them strategically in the tension zone of the H-piles to get a better bond. It's a really thought-through design.
Okay, so the design looks good on paper. How do they prove it works? Simulation.
Yeah, you got it. They built a detailed finite element model, FE model, scaled it at 1 to 3. It included everything: the concrete abutment, the composite dowel girder, the dowels, the rebar, the H-piles, like a digital version of that critical joint section.
A digital twin, essentially.
Pretty much. And they went into serious detail, really fine mesh, minimum element size of just 10 millimeters around the composite dowels to capture the stresses accurately.
Wow, that's tiny.
It is. And they modeled the interactions carefully, how surfaces touch, how friction behaves. Interestingly, they modeled the composite dowels and the girder web as a single integrated unit.
Which reflects how they're intended to work together.
Precisely. But the key thing with any model is validation, right? Does it match reality?
Always the crucial step.
So they compared their FE model results against data from an actual physical test done by someone else.
And how did it stack up?
Remarkably well. The load displacement curve from the simulation almost perfectly matched the experiment.
That's impressive.
It is, and not just the overall response, but how it failed. The model predicted the concrete crushing, the steel girder pullout, even the crack patterns very accurately.
So the model is reliable.
Highly reliable. There was a tiny difference in stiffness in one phase, the elastoplastic stage, but they had a good explanation for that, related to friction in the model versus bonding in the real test. So yeah, high confidence in the simulation.
Okay, that's the structural side. But bridges live outdoors. What about things like temperature?
Ah, yes. Temperature is huge, especially with steel concrete composites. They heat up and cool down differently.
Right, steel expands more than concrete.
Exactly. So the deck becomes really sensitive to temperature swings. And get this, under extreme heat or cold, the stress from temperature can actually be more significant than the stress from traffic and the bridge's own weight.
More than the dead and live loads.
Wow. Yeah,
Yep.
It can dominate. To get a handle on this, the study looked at 5 years of temperature data from Xi'an, max and min temps each month.
Real-world data.
They used a statistical method, generalized extreme value distribution, GEV, to figure out realistic extreme temperatures the bridge might see. Came out to 37.5 degrees Celsius max and 15.7 Cmin.
So about 100 Fahrenheit max and maybe 60 Fahrenheit min. That gives them the range.
Right. And with that range, you can predict how much the bridge will expand or contract. It depends on the bridge length, that temperature difference, and the material's expansion properties. Usually it expands or contracts sort of symmetrically from the middle.
So you absolutely have to account for temperature in the design.
No question.
Yeah.
Especially for these jointless designs where there's nowhere for that movement to be easily released.
Okay, so they have this validated model. They understand the temperature effects. The next step is usually optimization, right?
Yeah.
Trying to fine-tune the design.
Exactly. They ran a big parametric analysis, basically tweaking different design variables in the model to see how each one affected the ultimate strength, the bearing capacity of the abutment.
And what do they find? Any surprises?
Quite a few interesting things, actually. For instance, they looked at using stronger steel Q460 versus the standard Q345.
You'd expect stronger steel, stronger bridge.
You would. But the improvement in ultimate capacity was surprisingly small, like only 5.9% better for one girder size, 3.5% for another.
Really? That little?
Yeah, which is great news, actually. It means you can often stick with the more economical Q345 steel without really sacrificing performance. That's a significant cost saving.
That is a game changer. So stronger steel doesn't help much. What does help?
Increasing the width of the steel girder's base plate, the bottom flange, that made a big difference. Going from 500 millimeters to 600 millimeter wide boosted capacity by 12%.
Okay, so width matters more than grade in this case.
Seems so. It gives designers a clear way to boost strength if needed just by adjusting that width.
What about things like the thickness of the web or how far apart the dowels are spaced?
Interestingly, neither of those had a major impact on the ultimate capacity. The reason they found was that failure was governed by concrete crushing, not by the steel girder web reaching its limit.
So thickening the web wouldn't help if the concrete fails first anyway.
Precisely. It tells you where the weak point really is and where strengthening efforts will pay off.
Makes sense. And the dowel arrangements themselves. You mentioned the CL-shaped connectors. How they arrange them matter?
Oh, definitely. They tested 3 configurations, CL1, CL2, CL3. The winner was CL2, that's the one with 3 horizontal rows of dowels, spaced 100 millimeters apart.
3 rows.
Yeah. It gave about 2.3% more capacity than CL1 and over 6% more than CL3. And importantly, it's still practical to build. So CL2 is the recommended setup.
Good to have a clear recommendation. Now, what about reinforcement? The rebar in the concrete. Always critical.
Absolutely critical. And the results showed it clearly. They looked at the reinforcement ratio, basically how much steel bar is in the concrete, both in the abutment itself, let's call it ROS, and in the bridge deck slab.
ROS and more steel helped?
Significantly. Increasing earth in the abutment from 0.7% to 1.5% boosted capacity by around 11%, and increasing earth in the deck from 1% to 2% gave about a 13% boost.
Wow, so reinforcement is a major lever for strength here.
Huge. It really highlights you can't skimp on the rebar in these critical zones.
One last parameter, the width of the bridge section bearing on the abutment.
Yes, WCC they called it. They found a straightforward linear relationship, double the width, from 750 millimeter to 1500 millimeters, and you get about a 35.8% increase in bearing capacity.
So that gives engineers flexibility for different bridge sizes.
Exactly. You can tailor that dimension based on the specific project needs and load demands.
Okay, so that parametric study gives a great roadmap for optimizing the design. Now let's talk about failure. Understanding how things break is just as important.
Crucial. The FE model allowed them to visualize failure very clearly. They looked at strain contours in both the concrete and the steel.
And what did they see happening in the steel girder?
Well, the web part gets put under a lot of strain. The bottom plate and the ends get compressed. As you load it up, the internal forces shift, the neutral axis moves, and this causes the girder to rotate slightly.
Rotation. And that affects the concrete.
Right. That rotation starts to cause tensile cracks in the concrete web around the girder. And interestingly, the part of the web that's embedded deep in the abutment mainly experiences shear forces. It's quite a complex stress state.
And the cracks in the concrete, do they just spread randomly?
No, there's a definite pattern. They first appear as tensile cracks at the top of the abutment towards the back.
Right.
Then they spread down through the concrete around those composite dowels that's driven by the girder rotation and concrete compression. From there, the cracks tend to extend towards the bridge deck and also down towards where the girder meets the steel piles.
So a predictable path of failure.
Very much so. And ultimately, the whole thing loses its load-carrying ability in a few key ways.
Which are?
1, the concrete crushes right underneath the steel girder's base plate. 2, major cracking develops in that concrete web. And 3, the steel girder itself can buckle. Knowing these specific modes is vital for safe design.
Definitely. So we know how it fails. But how does it actually carry the load before it fails? What's the mechanism?
It's quite intricate. And here's a key insight. Those composite dowels on the web, they don't actually contribute much to the ultimate strength.
Really? I thought they were the main innovation.
They are, but their main job seems to be enabling teamwork between the steel and concrete. They enhance the collaborative load bearing. The stress within the dowels themselves stays relatively low.
Okay, so they're like facilitators.
Yeah.
Helping the other parts work together better.
That's a good way to put it. The actual heavy lifting, resisting the external load, is done mainly by 3 things.
Go on.
First, the concrete that sits between the composite dowels. Second, the steel rebar in the bridge deck slab above. And third, the concrete right at the contact surface with the main girder.
Interesting distribution.
Yeah, and it shifts. Initially, under lower loads, the bending is mostly taken by the steel girder's bottom plate. But as the load increases and things start to yield a bit, that elastoplastic stage, the load gets transferred more and more to the rebar in the deck slab.
So the rebar kicks in later.
Exactly. Until finally, that concrete under the girder base plate crushes, and that's pretty much the failure point for the joint. Oh, and the rebar running through the composite dowels mainly takes shear while the concrete around them is in compression.
It's a complex dance of forces.
It really is. But what's reassuring is the ductility.
Yes, you mentioned that.
No.
Meaning it doesn't just snap.
Right. Even after it hits its peak load capacity, it doesn't just suddenly drop off. The capacity decreases more gradually while deformation increases quite a bit. That's good ductility. It gives warning and avoids brittle failure. Very desirable in structures.
Absolutely. So armed with all this understanding, the optimization, the failure modes, the load transfer, did the researchers manage to boil it down into something practical, like a design formula?
They did exactly that. Based on their findings and some theoretical assumptions, they developed a predictive formula for the ultimate bearing capacity of this specific joint design.
And this formula actually accounts for all of those factors.
Yes, it incorporates contributions from the composite girder, the connections, and importantly, those key parameters like girder depth and the reinforcement ratios.
How accurate is it?
Remarkably accurate. When they compared the formula's predictions to their detailed simulation results, the average error was less than 3%.
Less than 3%. That's fantastic.
It really is. It means engineers have a reliable, pretty simple tool they can use for quick design checks, for optimization, and for assessing how the joint will perform under different loads, including temperature and seismic effects.
That makes the research immediately usable, which is great. Now, you mentioned cost savings earlier with the steel grade. Did this overall design approach show potential for material savings too?
Yes, and this is a really compelling point. They compared their design to a more traditional setup using a standard eye-shaped steel girder from another experiment, keeping things like girder depth and base plate width similar.
And the result?
Their integral abutment design, using the composite dowels and the MVFT girder, used 23% less steel.
23%? That's huge.
It's a massive saving. And it's not just cutting corners. The reason why is fascinating.
Why is it more efficient?
Because the longitudinal rebar in the bridge deck and the concrete web actually helps the steel girder keep carrying load even after the steel itself starts to yield. In traditional designs, once the steel yields, that's often it. Here, the system works together more effectively, allowing for a more slender, efficient steel section.
So the whole system approach allows for smarter material use.
Exactly. Better collaboration means less brute force material needed. It's a win for cost and sustainability.
Okay, let's try and wrap this up then. This deep dive really shows that this novel integral bridge abutment using these composite dowels, it's a pretty significant advance, wouldn't you say?
I definitely say so. It tackles those long-standing problems with expansion joints head-on. You get better durability, better safety, and it's more cost-effective over the bridge's life.
And we now have a much clearer picture of how it works, how it fails safely, how loads are transferred.
Right, the mechanisms are well understood now. And critically, there's that validated predictive formula to help engineers actually design and implement this. It makes it practical.
So it seems like a really promising path forward for bridge design.
It does. Which leads to a final thought, perhaps. We've seen how rethinking just one connection, that girder abutment joint, can cut steel use by almost a quarter and potentially lead to much longer-lasting, lower-maintenance bridges.
Yeah.
So it makes you wonder, what other hidden joints or maybe overlooked connections exist in our infrastructure, buildings, tunnels, other structures that could benefit from this kind of deep dive, applying innovative materials and smarter designs?
Like where else could we eliminate a traditional weak point?
Exactly. What could the ripple effect be for our communities, longer term if more of these kinds of jointless or just fundamentally smarter, more integrated innovations became the standard way we build things?